When thinking about the ever greater impact of machine learning, or AI, upon engineering science, we at ADT have considered very carefully how one might leverage the power of these algorithms to the specific and highly complex problem of turbomachinery blade design. A huge amount of engineering and computational resources goes into the design of turbomachinery, especially to meet multi-point, multi-objective, multidisciplinary problems. We observe that applying machine learning methods in design optimization studies can considerably reduce engineering and computational costs. Large language models require billions of cheaply available datasets, like text and images, so are not suitable for use in this context. Data availability for turbomachinery is very limited and mainly proprietary. Using legacy datasets is inaccurate, with out-of-date information or poor resolution leading to errors. And, in general, turbomachinery requires high-fidelity simulation data, which is very costly to generate. So, what do we need to build an expert system? We had identified the following pillar components: geometry parameterization, high-fidelity performance data, machine learning with small datasets leading to expert systems. Consider describing the complex shape of a centrifugal fan with a set of parameters. As the blade is highly three-dimensional, one might think that data on a large number of spanwise sections is necessary. The more sections used, the more complex the blade can be. Indeed, when using the traditional parameters of blade angle, thickness, and stacking distribution, this is entirely true. What it also means is that, in this traditional approach, an extremely large number of parameters is needed to describe the blade shape and provide enough flexibility in the geometry envelope to drive meaningful performance change. Moreover, once a new shape has been generated, there is no indication of performance for that design, even for the most basic duty requirements. For example, a target head rise for a given flow rate and speed. The first thing that must be done for each and every design is to assess its performance in CFD. By contrast, inverse design requires only a handful of parameters to describe a complex blade shape. The parameters are effectively performance demands, and the blade shape is the output of the given work distribution. The blade shape for a given parameter set is arrived at in a matter of seconds, along with surface pressure and velocity distributions, plus loss estimations. So, when starting to look for optimal designs, the 3D inverse design method is already at a distinct advantage. In this centrifugal pump study, geometries created by direct design scatter through the performance space, even with limits on exit blade angle. A lot of geometries give poor cavitation performance, as seen in low values of minimum pressure. However, every inverse design candidate is, by definition, going to meet the basic required duty. All candidates appear around the duty point, with only a plus or minus 5% head variation. The distribution of the work across the blade, which we vary by modifying the input parameters, will affect the efficiency and losses incurred in generating that work. This enables creation of accurate surrogate models for rapid multi-objective optimization. For multi-point studies, we need a seamless method for sending and retrieving high-fidelity CFD data to and from the optimizer. TurboDesign 1 integrates directly with high-fidelity simulation tools. It supports all turbo machine types. It is CFD agnostic. Templated methods mean a consistent analysis workflow. It supports local clusters and HPC. Automated meshing, pre-processing, simulation, and post-processing are activated with just a few mouse clicks. And multi-point results are integrated into the optimization process. Turning to methods for efficient optimization. Multi-objective optimization can be carried out by a multi-objective genetic algorithm. This is a well-proven approach and easy to understand and control by the use of metaparameters such as number of generations, crossover, and mutation probability. However, it has the distinct disadvantage of having to generate a large number of non-optimal candidates in order to provide enough variation in the population. To save effort, one might employ a low-order surrogate model to predict the design space topology. But surrogate models lack the accuracy of high-fidelity backed and can lead to false optima being identified. ADT eliminate the wasted effort of a genetic algorithm whilst retaining high-fidelity accuracy with the use of the reactive response surface machine learning algorithm, which can reduce, by orders of magnitude, the CFD cost and time of an optimization study. RRS begins with a sparse sampling of the design space using a Latin hypercube pattern. The model then discovers potential candidates that are close to the optimal objectives. As the new candidates are evaluated, they are added to the topology of the design space, making it reactive. For multipoint simulations, we assess performance in CFD, whilst the RRS optimization is ongoing. The combination of low-dimensional design space, performance specified as an input, targeted integrated use of high-fidelity simulation, and intelligent reactive design space exploration means that we can achieve orders of magnitude speed-up in the search for multi-objective, multi-point optimal designs, running on standard desk-side hardware, whilst exploiting even higher fidelity and multidisciplinary simulation. This technology is ready to go out of the box, with just a few mouse clicks to set up and run.